Welcome to the Biopharma Business Intelligence Unit, where symbolic integrity meets strategic clarity. At BBIU, we go beyond the headlines to decode the structural forces behind global biopharma, AI, and economic realignment. If you value precision, verification, and symbolic depth, this channel is for you. Subscribe now to access our weekly briefings, dossiers, and intelligence reports, and consider joining our institutional tier to unlock early warning systems, custom metrics, and exclusive strategic insight. You're not just listening, you're entering the future of epistemic intelligence. www.biopharmabusinessintelligenceunit.com.
BBIU White Paper, From Copper to Light, Q-Photonic Computing and the Path to Room Temperature Quantum Processors. Sep. 3rd, Executive Summary, https://archive.org/details Q-Photonic-computing. Quantum computing is often described as the next revolution in information technology. Yet its current implementations, especially superconducting qubits, face severe structural limits. They only function near absolute zero, and their energy cost lies not in calculation, but in refrigeration. Scaling these machines commercially would mean scaling cryogenic infrastructure, an unrealistic path. An alternative is emerging at the intersection of nanophotonics and quantum information science, Q-Photonic Computing. This paradigm uses photons as the carriers of quantum information, manipulated by ultra-thin metasurfaces known as metalenses. Unlike superconductors, Q-photonic systems can operate at or near room temperature, bypassing the energy bottleneck of cryogenics. Recent advances, such as the Samsung plus POSTEC ultra-thin metalens and Harvard's photonic metasurface processors, suggest that the transition from copper, classical conduction, to diamond, NV centers, and finally to light itself is not theoretical, but already underway. 1. The current bottleneck, superconducting qubits. Operating environment, millikelvin temperatures, maintained by dilution refrigerators the size of large industrial machines. Energy balance. Almost all the power goes into cooling, not into computation. The actual qubit operations consume negligible energy. Scalability problem. While 100 to 1,000 qubits are possible today, scaling to millions would require cryogenic facilities for every rack, which is economically and physically unsustainable. Commercial limitation. The technology works, but cannot escape the laboratory scale without a breakthrough in refrigeration or a move to a different physical platform. 2. Beyond diamonds and copper. Copper silicon, classical electronics, reached scaling limits due to heat dissipation and transistor miniaturization. Diamond NV centers allow room temperature qubits through electron spin defects in diamond. They provide proof of concept for quantum information without cryogenics, but are expensive, fragile, and difficult to mass produce. Trapped ions and cold atoms, high fidelity, but require large vacuum systems and complex optical control, limiting industrial integration. Each alternative highlights the core question: how can we move quantum systems out of cryogenic and vacuum laboratories and into scalable, manufacturable chips? 3. Metalenses, a nanophotonic breakthrough development. Samsung and POSTEC created a 2/3 wavelength phase delay metalens, published in Nature Communications, 2024. Engineering principle: nano-patterned metasurfaces bend and control light with sub-wavelength precision, replacing bulky curved glass lenses. Industrial viability, already demonstrated in smartphone and XR device prototypes, reducing camera module thickness by 20% while improving optical performance. Quantum relevance: if such metalenses can be adapted for coherent photon manipulation, they could become the substrate for room temperature quantum operations. 4. From qubits to high-dimensional qubits. A qubit is a two-state quantum system, analogous to a coin, heads 0, tails 1, or spinning in superposition. A qubit extends this to multiple states, 3, 5, 7, or more, each a valid coherent outcome. Metalenses can be engineered so that one photon is mapped into multiple distinct optical pathways, each representing a state. Key insight revised. Using a pentagonal design, one can illustrate how a photon might occupy 5 coherent states, d = 5 qubit. However, this is merely a pedagogical example. In practice, nanophotonic engineering allows dozens or even hundreds of phase channels per metasurface, yielding very high-dimensional qubits, d5. This exponentially increases information density and reduces the number of physical particles required to reach quantum advantage. 4 bis. Harvard's photonic research. Harvard has been at the forefront of quantum photonics, providing multiple proofs of principle. Quantum metasurfaces, flat processors where multi-photon interference and basic algorithms are executed without traditional bulk optics. Rydberg atom arrays, laser-controlled atoms arranged in programmable grids, demonstrating entanglement and simulation at unprecedented scales. NV center integration. Early diamond research at Harvard helped establish room-temperature spin-photon interfaces. Metasurface optics. Research shows that metasurfaces can replace beam splitters, interferometers, and lenses, shrinking quantum hardware into chip-level devices. Strategic link. These results confirm that photonic quantum architectures can bypass cryogenics. The trajectory described in BBIU's analysis, from copper to light, the rise of gravity-free quantum metasurfaces connects academic breakthroughs, Harvard, with industrial readiness, Samsung POSTECH. 5. Defining Q-Photonic Computing. To avoid confusion between classical photonic accelerators and genuine quantum platforms, we define photonic computing, classical, uses light to process information deterministically, e.g. optical neural networks. Fast and efficient, but not quantum. Quantum computing, general, uses quantum states, superconductors, ions, photons, spins. Encompasses all platforms. Q-Photonic Computing, new term, a specific branch of quantum computing where photons serve as the qubits, manipulated by nanophotonic structures, metalenses, metasurfaces, photonic chips. Value of the definition: preserves the Q for quantum coherence, distinguishes it from purely optical accelerators, positions it as a third structural path beside superconductors and ions. 6. Why this matters for the public. Lower energy use, eliminates massive refrigerators, cutting operational costs and environmental footprint. Cheaper machines, photonic metasurfaces can be mass-produced like smartphone chips. Scalability, uses existing semiconductor fabrication lines. Democratization, from exclusive labs to broader industrial and eventually consumer access. Strategic independence, countries or firms mastering Q-photonic platforms would leapfrog current leaders in superconducting architectures. 7. Road ahead phase 1 to 3 years. Metalenses Qubit simulations and prototypes, DUC 3, DUC 5. Phase 2, 3 to 7 years. On-chip integration with reliable single photon sources and detectors. Phase 3, 7 to 10 years. Universal Q-photonic processors with large-scale applications in AI, healthcare, finance, and climate modeling. Conclusion. Quantum computing today is technologically valid but structurally unsustainable. Cooling costs dwarf computation. The shift to Q-photonic computing via nanophotonic metalenses offers a pathway to room temperature, industrially scalable quantum machines. From copper, classical conductors, to diamond, NV centers, and now to light itself, the trajectory is clear. The next generation of computation will not be frozen in refrigerators, but encoded in photons, structured by metasurfaces. For an extended analysis, see BBIU's editorial, From Copper to Light, the Rise of Gravity-Free Quantum Metasurfaces. Annex, Practical Implications of Q-Photonic Computing. A. Real-world use cases, healthcare and medicine. In drug discovery, today's supercomputers can only approximate molecular interactions because the number of possible configurations explodes beyond their capacity. Quantum processors, especially Q-photonic systems with high-dimensional states, could simulate billions of molecular interactions simultaneously, cutting the time to design a new antiviral drug or cancer therapy from years to days. In genomics, entire human genomes could be processed within hours instead of weeks, making personalized medicine, tailoring therapies to the DNA of each patient, a practical reality. Climate and environment. Climate modeling is notoriously complex. Current models simplify ocean currents, atmospheric chemistry, and ecological feedbacks because no computer can integrate them all at full resolution. A Q-photonic processor could run integrated models of the entire planet in real time, producing more reliable forecasts of hurricanes, droughts, and other extreme events. In energy systems, these processors could optimize smart grids, balancing solar, wind, and storage with unprecedented efficiency, directly lowering costs for households and industries. Artificial intelligence training. Today's large AI models consumes enormous resources, sometimes measured in millions of dollars in electricity for a single run. A Q-photonic system, capable of encoding many more states per photon, could train such models in a fraction of the time and energy, dramatically lowering barriers to innovation. Beyond efficiency, hybrid architectures that combine quantum and classical logic might yield new forms of decision-making intelligence, closer to human intuition, but scaled to global datasets. Finance and logistics. Global markets involve millions of interacting variables, far too many for classical models to handle in real time. Quantum systems could evaluate these interactions simultaneously, producing more resilient forecasts and risk assessments. In logistics, the same principles could optimize international supply chains, choosing the most efficient routes, inventory allocations, and shipping schedules across continents, leading to lower consumer prices and greater stability in global trade. B. Comparative framework. Quantum technologies can be compared across four main dimensions: operating temperature, energy cost, scalability, and the number of information states each unit can represent. Superconducting qubits. These systems only work at temperatures close to absolute zero, in the millikelvin range. Their biggest energy expense is not the calculation itself, but the constant refrigeration, which consumes kilowatts continuously. While they have demonstrated very high fidelity, their scalability is severely limited. Replicating cryogenic infrastructure at industrial scale is simply not feasible. Each qubit can only encode two states, 0 and 1, so the information space grows linearly. A fitting analogy would be a race car, fast and precise, but one that can only operate inside a gigantic freezer. Diamond NV centers. These allow qubits to function even at room temperature, though they require precision lasers and extremely expensive materials. They offer a glimpse into the possibility of quantum systems without cryogenics, but mass production remains extremely difficult, limiting industrial deployment. Moreover, they can only handle a small number of states, 2 to 3. They resemble a luxury watch, elegant and precise, but far too costly and complex to produce at scale. Q-Photonic Computing with metalenses. Here, photons themselves carry the quantum information, and their behavior is controlled by ultra-thin metasurfaces. The advantage is profound. These systems can operate at room temperature with minimal energy use, since they do not require massive refrigeration or vacuum chambers. Their scalability is high, because they can be manufactured using the same industrial processes that already produce semiconductors and consumer optics. Most importantly, a single photon is not limited to two states. Depending on the lens design, it can represent 5, 10, or even hundreds of coherent states, making information density grow exponentially. The best analogy is the smartphone camera module, tiny, inexpensive, produced by the millions, yet here with the potential to form the core of a quantum photonic computer. See social and economic impact. Energy savings reverses the imbalance. Power goes to computing, not cooling. Democratization, from corporate labs to universities, startups, and public institutions. Geopolitics, a decisive edge for nations leading Q-photonic platforms. Public perception, making the leap tangible. The same flat lens that shrinks your smartphone camera could also power the next quantum computer. Final note, Q-photonic computing is not simply an incremental improvement. It is a structural redefinition of quantum architecture. By embedding coherence into light manipulated by metasurfaces, it offers exponential efficiency, industrial manufacturability, and a direct path to room temperature quantum advantage.